And now you're recording. So now you can just do your thing. And at the very end, you'll click this icon at the end and then pause it. Yeah. Okay.
Thank you.
Mm-hmm.
So do you want to start? I haven't looked at this question. I know what we can do. We can just put the pandas question. Yeah, before you start.
Two slides.
Yeah, but like before you start your logistic regression.
Or just put it right before logistic.
Yeah.
Right after this.
Oh no. Wait. I messed up. I will put it right before the break.
Yeah.
And then... Okay, it should be good now. Okay, then let me start. Do I need to use the mic?
Sam said to repeat the question.
What?
Sam said to repeat the question. Before, if someone has a question, repeat it so that we can read it.
Oh, okay. But, I don't know. Okay. Okay. Hi everyone. Hi everyone. Does the mic work? Yeah, good. Okay, welcome to the first part of the final review. Me, Manana Hakokman, and Stephanie will do the review for you today. And there is the second part for tomorrow, Tuesday, so make sure to go to that one as well. Let's start. So we put the overview of topics we're going to touch or like cover like little in depth today, and those are going to be pandas in SQL, regex, EDA visualization, dimensionality reduction in PCA, random variables and probability distributions, risk and loss functions, logistic regression, classifier evaluation, decision trees, and random forests. And we put this slide so when you go home, you open this slide and read every topic and say, okay, do I know this? If I don't, I need to go through this again before tomorrow's review section. And then the agenda for today is we'll do some pre-midterm reviews stuff, so like pandas, SQL, regex, and the way we will cover it, we will just have questions and we'll do it together. It's either true or false questions or some like very simple coding questions. And then we'll cover logistic regression, classifier evaluation, and decision trees more in depth, because those are, like, you voted for these ones in the poll in Piazza. Okay, so one thing, I use these little like cartoons from Chris Alban, and those are like very fun and like very simple. I recommend like reading them. So this is about PCA, principal component analysis, and it says that basically we use principal component analysis for dimensionality reduction, and the way it shows here, we have like we take the direction of the highest variance and as the first principal component, and then the second principal component is orthogonal to that and takes like the second highest variance direction. Okay, so first true or false question. PCA can be used for projecting and visualizing data in lower dimensions. True? True? Okay, so this one is true. We're not even reading the false for this one. Okay, second question is, the most popularly used dimensionality reduction algorithm is principal component analysis. Which of the following are true about PCA? And I'm going to give you 2 minutes to read the statements. Okay, let's do this one. So the first statement is PCA is an unsupervised method. Is this true? False? Okay. Second one, it searches for the directions that data have the largest variance. True? Good. Maximum number of principal components is less than equal number of features. True. Good. All principal components are orthogonal to each other. Okay. So one thing you were not sure was the first one, is that PCA is an unsupervised method, and it is an unsupervised method because you don't train it or like do anything with supervised data, so it just like works unsupervised. It's like a new idea, as it was not in the lecture, so I'm not going to be harsh on that. I just put it as a fact, so you know before the final. Okay. What happens when you get features in lower dimensions using PCA? Take like a minute to read the statements. Okay, let's read it together. The first statement is the features will still have interpretability. Can we interpret the features after reducing them with PCA? Is this true or false? True? False? Okay. The features will lose interpretability. It's like the same question, same statement, just tweaked. The feature must carry all information present in data. True? False? Okay. The features may not carry all information present in data. That's like the tweaked way. Okay, great. Okay, let's look at the correct answers. So the correct answers for this one is actually the second one, that the features will lose interpretability. It's because when you're doing PCA, you're taking the linear combination of your features that present the highest variance. So once you like add them or like multiply with them with some scalars or something, they kind of lose their interpretability. And then the fourth is correct because features may not carry all information present in data because you might reduce the dimensions and lose some information. But you still do your best to take the highest variance in your data. Yes? Unless you take the feature itself, it loses the interpretability. Okay. This one. Imagine you're given the following scatter plot between height and weight. Select the angle which will capture maximum variability along a single axis. Okay, I will read the options and then you raise your hand whenever you think the option is right. So A is 0 degree. Great. B is 45 degree. Amazing. C is 60 degree, D is 90 degree. Those are not correct. So as we said, B is 45 degree. Because like, if you look here, the highest variability dimension will be lying along 45 degree angle. Okay. For this one, I will give you 2 minutes to think about, and it asks you which of the following can be the first two principal components after applying PCA. It has a little trick. Okay, let's do this together. Who thinks the first one can be the PCA component? Second one? Third one? And then the fourth one? Okay, whoever said it can be the third one, can you explain why? Is there any volunteer? Yes?
Principal components have to be orthogonal, right?
Yes.
So that means the dot product of two vectors has to be 0. Unless I'm really bad, which is true. I think the dot product is 0.
Okay, great. That's exact reason. The principal components need to be orthogonal to each other. And what it means in linear algebra world, it means that the dot product needs to be 0. And for both third and fourth options, if you take the principal dot product of these two vectors, you'll get zeros. So they can be principal components after doing the PCA. Okay, we hit this one too. Okay. Suppose X is a 100 to 5 matrix with rank 3. What are dimensions of U, sigma, and V? Take a minute to think about it. This is a little hint. Okay, let me do this with you the way I think of it. I start with the sigmoid, like the singular values. Because the rank is 3, we're going to have 3 distinct singular values. So if we start from this one, we will know that in the middle of this decomposition, we have 3 by 3 matrix. And we know that we want to get X, which is 100 by 5 matrix. So the first number in the decomposition needs to be 100. So U automatically becomes 100 by 3, because 3 needs to match with the singular values, 3 by 3. And then what we're left by is V transpose. And then V transpose needs to start by 3, because it needs to match with the singular values matrix. And it needs to end with 5, because that's what's the end of the X matrix. The only trick that you want to remember is that V is in transpose. So you want to transpose it back and say that V is 5 by 3 matrix. Okay. That was like a very quick overview of PCA. Let's do probabilities and RVs. Here a question for you. Let me read the question and then I'll give you like 2 minutes to think about it. So Kelly wants to measure interest for a party on her street. She assigns numbers and letters to each house on her street as illustrated above. She picks a letter A, B, or C at random and then surveys every household on the street ending in that letter. Actually, I haven't put this question here from the exam, but what will be the kind of the sample? Give me an answer. Yeah. Okay, say it all. Cluster. Yeah, so it will be cluster sample because you will divide it into clusters and just take one cluster. So for the remaining parts of the question, suppose that 1/2 of the houses ending in A favor the party, 3/4 of the houses ending in B favor the party, and all of the houses ending in C favor the party. Hence, overall, P is 3/4 of the houses favor the party. If Kaylee estimates how favorable the party is using the proportion P estimate of households in her survey favoring the party, what is the expected value of her estimator? Okay, take 2 minutes to discuss with your neighbor and think about it. Okay. Does anyone have the answer? Do you want to try? Just out of curiosity. Okay, I'm showing the answer. It's 3/4. And the way you think about it is that the expected value of the estimator is the weighted average of the estimations in the groups, and you have 3 groups, and each of the group has like equal weight in your sample. So you have 1/3 A's, 1/3 B's, and 1/3 C's. And then the way you do it is you say, so 1/2 of the 1/3 favors the party, plus 3/4 of the 1/3 favors the party, and then the whole 1/3 favors the party. So you have overall 3/4 favoring the party as estimation for the sample. Is this clear? Okay, I've seen some nodding. We go ahead. There is a second question. If, as before, Kaylee estimates how favorable the party is using the proportion P hat of households in her survey favoring the party, what is the variance of her estimator, variance P hat? Okay, let's do this together. So, actually, a question. What is the definition of variance? What? Data? Okay, so yes, variance is a measure of spread, but the way we define it mathematically is we take the expectation of the squared values of the estimations of the expected values. Okay, this was very complicated. But the way we write it mathematically is that you have your estimated P proportion and you have your observed proportions, and every time you're taking the difference from your estimated proportion, and then you take the expected value of these differences. So what you need to do is that from the previous question, we know that your expected P hat is 3/4. So you're taking the difference from these 3/4 for each letter. So in this one, where you have 1/2, you do 3/4 minus 1/2, and you get 1/4, and then you square it, and you get 1/16. And then for the second one, where you have, I believe, the 3/4 favors in B, 3/4 favors the party, so you do 3/4 minus 3/4 squared, which is 0 squared, and it's 0, it comes here. And then you do 3/4 minus 1, which is minus 1/4, but when you square it, it becomes 1/16, so it falls here. And then because you have equal weight of each cluster in your sample, you divide everything by 3. And you get 1/24. Is this clear? Okay, Then let's jump to loss functions. Take 2 minutes to read the question, and then we will discuss the statements together. I think this is the last question. Am I doing good on time? I think so. Okay, I'll keep this short. Okay, let's discuss the statements. Who thinks that there are d data points for this given loss function? Who thinks that there are n data points? Okay, great. And the way you know about it is that here, where you're summing the loss function over all data points, you see that you have n data points. Okay, who thinks that the data is d-dimensional? Raise your hand. It's d-dimensional. So the way you see that is that you regularize kind of your features, which are the dimensions of your data, and you see in this regularization term that you have d, like you sum over d, so you have d dimensions. Okay, this is a classification problem. Who thinks it's a classification problem? Amazing. This is a linear model. Yes, and the where, like, it's this part in the equation that signals you, not the equation, the loss function that signals you. This problem has lasso regularization. Okay, this is not lasso regularization. This is ridge, and the way you see it, you have square. Lasso is with absolute value. Larger values of, is it lambda? No, what is this? Lambda. Lambda imply increased regularization. Yes? It's true. The larger this term, the larger the regularization. Larger values of lambda will increase variance. Oh no. Okay, this one is not true because you regularize to avoid overfitting, and when you have high variance, you have overfitting. So regularization actually decreases variance. Larger values of lambda will likely increase bias. True? True. If the previous statement was false, this one needs to be true because variance and bias go opposite directions. And then J is none of the above are true. This is wrong. Okay, this is the answers. I'm giving you a minute to have any questions about this one. Okay, if no questions. Oh, I put here a note. So remember, every time you're given a loss function and you want to optimize that loss function, you need to take the derivative or gradient and then set it equal to 0. This is like a fact. And I have like illustrations here, like look at them when you're looking at the slides. One is about mean squared error, and then the other one is mean absolute error. Okay. Stephanie is going to take over this question. Yes? Not yet, because we have the answers in the slide. We'll post them later.
Okay. Hello? Can everyone hear me? Okay, cool. So we're going to move on to a pandas and SQL question taken from last semester's final. So go ahead and take some time to work on this. Okay, who wants more time to work on this? And who wants to go over it? Okay, let's go over this. So we're building a table with 1 row per homework containing the total number of points scored by undergraduates on that homework. So the first thing to notice here is that we can't get all of this information in one table. So we have to combine them somehow. So in Python, what could you use to combine these two tables? Just shout it out. Merge, exactly. Cool. And then what would you merge on? Yeah, exactly. You want to merge on the undergraduate's SID and the IDs in the scores table. Okay, so we do exactly that, where we take scores and we merge that with UGrads on those two columns. Now, once we combine these two tables, we need to somehow still aggregate our score. So we group by our homework, we take our score, and we sum that up. For SQL, we do something similar, except now that sorry, waiting for this to come down. Oh no. Okay. Oh, that's really small. Okay. We are taking our SQL query, we're selecting homework, and we're summing our score. And then we also have to combine these tables. So we're taking our scores and joining it on UGrads on the same two columns with the student ID numbers. And then we are also grouping by homework because in the end we want to get our total homework score. So you use left index. Oh, the question was, can we use left index and right index? And with left index and right index, you would actually need the indices of the tables to be the thing that you want to join on. So in this case, because the ID and SID are just columns of the table, we want to use left on and right on. That's a great question. Any other questions? Yes?
Could you also do like the nested SQL statement, like where ID and select SID and grad group by homework?
That's something you could try. It's probably not the simplest solution, but yeah, it's something you can try on your own time. Good question. All right, so let's move on to attendance. Okay, let's come back together as a class and move on to logistic regression. So just a quick note, we aren't covering linear regression in this lecture because that's too much to fit in one day, but we will kind of assume knowledge of like very basic regression concepts. So a key distinction here between regression and classification is that regression is when we're trying to create a model that takes in a point and then outputs some sort of number. So this can be least squares, ridge regression, or lasso regression. Whereas classification is the problem of creating a model that takes in a point and outputs a discrete label. So for example, if we were to use a linear regression model, maybe we would try to predict a student's final grade given their midterm and homework scores. Whereas with classification, we want to say whether or not a patient has a disease, and we're putting a label on something. In this class, we'll mostly care about binary classification, so we'll work with zeros and ones a lot. So we have this handy function called the sigmoid function. And what this does is it takes any number in the real domain and maps it to a probability between 0 and 1. By definition, our sigmoid is 1 over 1 plus e to the negative x, which can also be rewritten as e to the x over 1 plus e to the x. So we have this cool symmetry with the sigmoid function, where the sigmoid of negative x is also 1 minus the sigmoid of x. And that's a useful property if you want to maybe do some calculation tricks, or it's easier to calculate one than the other. Another cool property is that the derivative is defined by the sigmoid function itself. And so how does this come into play with logistic regression? Well, in logistic regression, we want to look at the probability that we classify something as 1, given our x value. So that's where we get this probability of y equals 1 given x on the right side of the screen. And this is equal to 1 over 1 plus e to the negative x times theta. And this is just the output of our linear regression model. So this is saying that whatever we have from linear regression, that's a real number. Then we're inputting this real number into our sigmoid function so that we get a binary prediction between 0 and 1. And so that's how we get our sigmoid. If we are computing the sigmoid of x times theta, as our absolute value of theta increases, our steepness of the curve also increases. So this line over here will get steeper, and you'll have a curve that is not as flat. And negative values reflect the curve over the y-axis. Any questions here? Okay, moving on. Now, with logistic regression, we have to find a way to define how well our model is performing. So this is where cross-entropy loss comes in. This is the loss function that we use when we want to see how well our logistic model is performing. So in order to find our theta coefficients, we want to minimize this loss. So just like any other loss function, you want to find the values of theta that give you the least loss. And just for a notation thing, f of x here is our logistic model or our predicted probability. So oftentimes it will just be your sigmoid of x times theta. So one thing with cross-entropy loss is that we can't actually find an analytical solution for this. So we use other methods such as gradient descent. How would we find risk? Does anyone want to raise their hand? Yes. So that is the definition of risk. But in the context of cross-entropy loss, we want to define risk as the average loss across all points. So what we do is we calculate the cross-entropy loss for each point, and then we take the average of all of their losses to get our risk. And we'll have some practice with this in just a moment. Okay. So here are some true-false questions. Go ahead and think about them for a minute, read through them, and then we'll go through them together as a class. Okay, let's go over this. So the first question is asking us about a training dataset where we have 98 dog pictures and 2 cat pictures. Who thinks that it should always be possible to train a classifier to achieve 98% training accuracy? And who thinks this is false? So this is actually true. And the reason is we're only looking at the training set when we're looking at this 98% accuracy. So if we always predicted dog for every single classification picture, then we could hypothetically get 98% training accuracy. This does not hold true for the test set because we have different data in the test set. So who thinks that the second statement is true? A classifier that always predicts 0 has a test accuracy of 50% on all binary predictions. Who thinks it's false? Great. Yeah, so this is false because we could have class imbalances where there's less than 50% of data representing a 0. Or we could have a class imbalance in the other direction where we have a lot more zeros than ones. And lastly, while training a logistic regression model with gradient descent, we may converge to a local minimum and fail to find the global minimum. Who thinks this is true? Who thinks this is false? So this is actually false. And the reason for this is that the cross-entropy loss is convex. So any minimum we find will be the global minimum. Any questions on that? Yes? Yeah, so the question was, can you explain global and local minimums? So when we take derivatives or when we have functions, we have something that looks like this usually. And okay, so we might have 2 different examples of functions where we have just a parabola and then we have like a wavy U shape. When we have something that's convex, we can do a 2-point line test. So we take 2 points anywhere on the curve, and the line that we draw should always lie above the function. So for a function that's not convex, we can draw 2 points, and our line will fall under the curve. So this function is not convex, and when a function is not convex, then we can have multiple minimum. So we have a local minimum here and a local minimum here. So there's 2 different places where you could have a minimum point, but you might never know which one is the actual one, because if you're running something like gradient descent, you might get stuck here. When you have a global minimum, there's only one place that is the lowest point. And this happens when you have a convex function. Does that answer your question? Okay. Any other questions? Yes.
Can you just explain why we can only find a global minimum on unprobable functions? Like for this one, why can't there be a global minimum?
Yeah, so the question was, why can't we find any local minimum? And the reason for that is when we have cross-entropy loss, the function is convex. So whatever minimum we find is the global minimum. Any other questions? Okay. So let's move on to another question from last semester's midterm 2. Okay, does anyone want more time on this question? Okay, I will actually be going over this on the whiteboard or blackboard. So let's come over here. Can everyone see this, by the way? All right, really big. Okay, so the first idea here is we're working with finding the empirical risk. So the first thing that we need to start off is with our cross-entropy loss. So we can define that as negative y times log of theta minus 1 minus y of log 1 minus theta. So now that we have our loss, we want to look at each of the points that we have. So with cross-entropy loss, we're calculating the loss for every single point and then averaging that out. So we have the information that the probability that y equals 1, given that x equals 0, is equal to alpha. And we have this information also that the probability that y equals 0 given x plus the probability that y equals 1 given x is equal to 1. So we know that if these equal alpha, then the opposite should hold true, so that we have the probability that y equals 0 given x equals 0, and the probability that y equals 0 given x equals 1 should equal 1 minus alpha. So that when we sum up this term right here, we get 1. Any questions so far? Okay, so now we go on to calculate our cross entropy loss. We have our counts of the number of points we have for each of those xy pairs. So for our first xy pair, we have 2 times 0, 0. So this is our first probability here. And so we have our y term is equal to 0. So we can ignore this first term of our cross entropy loss, and we move on to the second term. So we have negative 1 times our log of 1 minus alpha. And then we have 3 over second point. So we have 3 times 0, 1. And so since x is 0, y is 1, we can cancel out our second term of our cross entropy loss and use this first half of the term. So we have negative 1 times log of alpha. And then we can do the same for the other 2 points that we have. So we have 1 of our 1, 0. And so we get negative log of 1 minus alpha. And we have 4 of our last point, which is 1, 1. So we have negative log of alpha. So we have 4 different losses right here, and we're multiplying these by the number of points that follow this loss function. And once we have all of these loss functions, we want to average our risk. So now, let me pull up the solutions. So when we average these out all together, we have negative 7/10 of log alpha minus 3/10 log 1 minus alpha. And we get this by adding up and multiplying all of the losses that we just got. So I won't go through the math there because hopefully you know how to take an average. But if you have any other questions, you can come to office hours or ask me after class. Any questions on this? Yes.
Does the loss function not have like a 1 over n already in the equation? Because on the slides that you were just on, the loss function had like a
Yeah, great question. So this is if we're summing up all of our loss functions. So actually, that's a great point that you made. This loss is representing the average loss across all points, whereas if we want to calculate the loss for a single point, we would just take this the part that's in the summation.
So this is calculating risk?
Yeah, so this is calculating risk.
aren't we summing, like, you just did 4 times like 1, 1. Isn't that essentially summing?
Yeah, exactly. So we start off by calculating the loss for each point, and then we can sum everything up and average that. And that's how we get our loss, or our risk.
Is it risk average though? I'm saying, I feel like the 1 divided by, I'm just confused, because isn't the 1 divided by n here already getting the average in this loss function? Isn't like this loss equation already getting the average loss?
Yeah, so you're correct that this function right here is calculating the average cross entropy loss already. So this is already our risk. Yeah, good question. Okay. Yes, question.
When you were doing that problem, why are you using alpha interchangeably with theta? Isn't it normally like sigma?
Yeah, that's a great question. So in this final, the formula that they give is that the loss here for a single point is theta. And so when we calculate our loss for the question, then we're given the information that this probability that y equals 1 given x equals 0, and the probability that y equals 1 given x equals 1 is equal to alpha. So because we're already given this value, we know that when we're calculating our loss here, that alpha is a term that we need to substitute into our loss function. And the idea is that our loss function would usually take a sigmoid function, but we already have a value that they've given us for the probability. So like the sigmoid function would tell us the probability or the odds that something is equal to 1 given our x value. But since we already have these alpha values given to us, those are the values that we input into our loss function instead. Good question. Anything else? Yes?
Will that equation sheet that you just showed us be part of our reference sheet?
I'm not sure yet. Last semester we put equations on the final, and I'm not sure if we'll do the same for this semester. But we'll let you know if we give you the equations or not. Good question. Okay. So moving on. Let's talk about classifier evaluation now. So we have classifiers that are functions that output a prediction for y. So it either gives 0 or 1 in some cases when we're predicting things. The problem with a classifier, like the sigmoid function, is that it doesn't tell us where the cutoff is for when we want to classify each category. So we have to come up with our own decision rules. And the simplest one is that we split it at 1/2, where if the probability that y is equal to 1 given our x value is greater than 1/2, then we classify it as class 1, otherwise we class it as the other class. So we have some evaluation metrics like accuracy, precision, and recall that help us evaluate like how well our classifier is performing. We have this confusion matrix that hopefully you're familiar with already. And we have other metrics like precision and recall when the accuracy isn't good enough. For example, if we have 900 values of one class and then 100 values of the other class, we might have a high precision just because we have a lot of the same value. So we use precision and recall when accuracy is not a good enough metric for us. A quick way I like to think about precision is it's the percentage of selected results that are relevant. So out of the ones that we have, how many of these are actually correct? And then recall is the percentage of relevant results that are selected. So out of all the true ones, how many did we actually choose? We use these false positive and true positive rates when we make our ROC curve. So our goal when we find our decision cutoff is to maximize our true positive rate and also minimize our false positive rate. So there's always a trade-off, but we can try our best and visualize this trade-off by an ROC curve. So here's some practice for you. Go ahead and read the question, and we'll go over this in about a minute. Okay, who thinks classifier A is better? Who thinks classifier B is better? Who doesn't know? Okay, so if we have 0% accuracy on our data set, what we can do is we can just flip every single result, and then suddenly we have 100% accuracy. So in this case, classifier A would be better because classifier B would just be like random guessing. So trick question here. Try this question on precision and recall. Okay, who thinks we should use accuracy? Precision? Recall? Great, yeah. So we want to look at recall because recall will tell us how many of our actual ones we're selecting out of the total number of ones. Okay. And lastly, try this question on classifying goats. Okay, does anyone want more time? Great, let's go over this. So we have 12 true images of goats, and we predict correctly 9 of them. And then we have 11 images that do not contain goats, so we predicted 3 of them to be goats and 8 not to be goats. So our precision is defined as our true positives over all positives that we classify. And so in this case, we have 9 true positives here, and we divide this by 9 plus our false positives, which is 3. So in this case, we have 9/12 or 3/4 as our precision. For our recall, we define this as our true positive rate divided by true positives plus false negatives. So again, our true positive is 9. And we have 2 false negatives. So we have 9 over 9 plus 2, and we get 9/11ths as our recall. Any questions on this? Okay. Hopefully that gave you a good overview on precision and recall. We are now going to switch it over to Manana.
Yes.
So the false negatives are 2 because these are things that we classify as not goats, even when they should be goats.
Okay. Let's move forward to decision trees, and let's actually look at this illustration together. So it says decision trees have high interpretability. After being trained, you can literally draw them. And here is a drawing of splits of your data via decision tree. And it says, okay, let's take one node and split it into female and male. And the drawing is actually sad because after it decides that it's female, it says the leaf is going to predict it to Cancer. And then males have like a little better chance. If it's like age is less than 30, I think it's no Cancer. And if it's it's Cancer. And if age is like more than 30, it's no Cancer. And this is exactly what decision tree does. It takes the data and just splits it with nodes. Okay, now some facts that you need to know about decision trees is that they're nonlinear algorithms. They're used for classification and regression. They work with both numeric and categorical data, and you don't even need to do extra feature engineering work in that. And then it splits training data into nodes, and we say node is pure if all the points in the node belong to the same label. So let's say if you have like 2 different classes and those are the classes you're trying to predict for, if your one node gets only points from one class, then that node is pure. And then we use this concept of entropy to calculate the loss of the split and the information gain. And we say that entropy is a measure of disorder or like messiness in the node. So from this statement, we can say if there is only one class in the node, so there is complete order in that node, right? So the entropy is 0 there. And then good nodes are lower entropy, so like has like less messiness. Okay, essential slide discusses the entropy, loss of a split, and information gain, and basically the formulas of calculating them. So the entropy of one node is the proportion of that class times the log of that class and then summed up. So if you have like 3 classes, you will have 3 summation categories, each containing the proportion times the log 2 base proportion. And then the split of entropy is taking the number of the points in that class and multiplying it with the entropy of that node, and then adding the number of points in the different class and adding the non-class node, and then adding the entropy of that child node, and then dividing it by the number of the points of the parent node. And like in a minute, we'll have practice, so you will use these equations on your own. And then the information gain is the entropy of the parent node minus the entropy of split. So like L split. Okay. And this is the practice I was talking about. You have seen something very similar during the lecture, but I thought it would be useful for you to do this again, like take like 2 minutes to try to calculate them on your own. Disclaimer, I have not seen the final, but I think this is something easy to test about the concept of entropy or like calculating, so put some energy into it. Who needs more time to do the calculations? Who wants to do it together? Okay, let's do it together. So all the solutions are here. So the parent node entropy is the proportion of the first class times the log 2 of that class proportion, and then minus the proportion of the second class, and then times the log of the proportion of that class. So in this case, we have 40 over 100, which I believe is 2/5, and it's like minus 2/5 times log 2/5 minus 3/5 times log 3/5, and I calculated for you 0.97. Then when I wrote first node, I meant the first child node, and here we have 2/3 D's and 1/3 B's, so the overall entropy will be minus 2/3 of log 2/3 and minus 1/3 of log 1/3, which is 0.918. And then for the second child's entropy, we have 2/7 of D and 5/7 of B, so we have the entropy equal to 0.863. Okay. Putting this in our loss function is that we see that we have 30 points in our first child node and 70 points in our second child node, and then we have overall 100 points. So that's where these 30, 70, and 100 come from. And then 0.918 corresponds to the entropy of the first child node, and then 0.863 corresponds to the entropy of the second child node. And remember that all the logs are 2-based, because we do binary splits. And overall loss of the split is 0.8795. Can you go away? And then the information gain should be the parent node's entropy minus the loss of the split. So the information gain is very little in this case. It's 0.0905. So the split was not as good. Generally, when you're splitting, you're trying to get the one that gives you the least loss, and then the highest information gain. Okay. Problems with decision trees. It's possible, sadly, to get 100% training accuracy. And what it means is that your decision trees can heavily overfit. And we need to think about some solutions, how to deal with these problems. And I said, fix it by setting maximum tree depth parameter, prune the tree, so just like get rid of the parts of the tree that are not useful, or use bagging. And bagging is a very clever thing. From the lecture, you know that they discovered it here in Berkeley. And random forest is an algorithm that uses this idea. So bagging is the bootstrap aggregating the training set to T sets, which means that you just bootstrap different sets from your training set and feed different trees, technically. And in random forest, you usually use different subset of features for these different T trees. And individual trees overfit, but they overfit in different ways because now you feed them with different features and with different subsets. So at the end of the day, because you have different variance trees and they overfit differently, you can achieve lower variance. To predict, you're asking these T trees, to vote, and then you take the majority vote. And this is the principle of most of the ensemble methods. Okay, here a cool illustration about random forests. So you see, like you get different subset of training set, and you have like different feature set, and then you feed them, and that's why you have these different trees. And then all of these trees vote, and then at the end, you take the majority vote. And technically, that's what it is. Okay, facts you need to know about random forests. They predict both regression and classification. No extra work with feature selection as with other tree methods. And then this one is good too because you can get nonlinear boundaries without feature engineering, so that you don't need to use like polynomial features to get nonlinear boundaries. And then it does just better job than decision trees because it doesn't overfit. It fights against overfitting. Okay, here a question. Take a minute to read the question. Okay, let's do it. In random forest, you can generate hundreds of trees, say T1, T2, like till T end, and then aggregate the results of this tree. Which of the following is true about individual TK tree in random forest? The first statement says, individual tree is built on a subset of the features. True or false? True. Great. Individual tree is built on all the features. This should be false automatically. Individual tree is built on a subset of observations. Yes, true. And then individual tree is built on full set of observations. False. And this like first sentence of the problem is what we call just short bagging. And then we see, and yes. And then one last question before I say bye to you. Okay, let's read it. How to select best hyperparameters in tree-based models. And it says tree-based, but it technically works, the logic works for all the models. A, measure performance over training data. Yes, no. This should be no. Never trust your training data. You feed the model on training data, but you always measure your performance on test data or validation set. So I just gave out the answer, is B. You're measuring the performance on validation set. And we're done on time. So you can stick and ask questions, but otherwise, good luck on the final, and don't forget there is final review part 2 tomorrow.